Okay, so we've looked at how to incorporate calculus into our graphs. Now we're going to have to pull back some of the review stuff from functions class. Asymptotes specifically. We've dealt with asymptotes a little bit with some of our limit stuff, but we haven't actually put them in graphs in this course. So again, we're just going to tie in what we've seen this year, what we're trying to do incorporating the calculus with some of the stuff from before. And so this is basically just going to be a review today. I have asymptotes VAO, vertical and horizontal, VHO, will be a review for sure. Obliques I'm not too sure about, so we'll cover obliques a little bit more detail. So if I just kind of look at a few examples here, instead of having you do this yourself, I just thought I could kind of pull up some quick examples. So 1 divided by x minus 4 gives us what is deemed a vertical asymptote right here at, oh, what a surprise, when x equals 4. Okay, so what you can see obviously is that when x is 4, we have this division by 0 in the denominator, and that's where our asymptote occurs. If we follow this graph up, we see that we're approaching 4, and if I continue that up, we never actually hit the 4, but we get closer and closer. Same thing on this side, I'm getting closer to 4, and even if I go quite a ways out, or quite a ways down, I don't know how it's going to let me do this, but 3.9. Now, unfortunately, the limitations of the graph are that it only goes a couple decimals deep, so it looks as if we're hitting the 4 with some of those, but we certainly don't. If we look at a second example here, same sort of thing. We have, again, what looks like a clear vertical asymptote at x equals 4. Maybe what I'll do is I'll actually put, oh no, sorry, x equals 4 in, and we'll graph it, and you can see the line kind of goes right up the middle, and that's again, that's going to be the vertical asymptote that the other two lines are not actually making contact with. Or these two sections of the graph are not making contact with. What we see this time though is there's another line here where this graph is, this section of the graph is staying kind of above and flattening out, and this section is staying below and flattening out. And of course that's going to be what we call the horizontal asymptote. The horizontal asymptote, it turns out in this case, is at y equals 3. And the reason the way we figure that out is basically the horizontal asymptote, as long as we have the highest power in the numerator being the same as the highest power in the denominator, those are the values that matter. And so essentially what's happening is as my x values get extremely large, my graph is getting really close, or my value of y is getting really close to 3 over 1. So again, if you put in 3 billion here, we have 3 billion divided by 1 billion minus 4, which is essentially just 1 billion. I suppose it's 999,999,996, but again, very close to 1 billion. And so we're getting an answer that's really close to 3 over 1. And so that's how we determine our horizontal asymptote. If we continue on here and look at the next one, I didn't need to leave that in, although it's fine. Essentially, we have a similar situation here. I'm going to zoom this one back in, actually, but quite a bit, because there's some interesting things going on here. Maybe not that much. Our vertical asymptote, x is -1. Again, looking at the denominator, pretty straightforward. If a value of x would cause me to have a division by 0, we can't allow that. Those are restrictions going back to, I guess, grade 11. Same sort of thing here still, though. At -1 itself, I can't actually calculate a value here, and so there's a vertical asymptote. Normally, of course, we will sketch a vertical asymptote in with a dotted line. Desmos doesn't offer me that option. So I just draw them in myself, but we recognize that that's not actually part of the graph. So if I put one in here at x equals -1 and graph it, again, that's representing my vertical asymptote. I would dash it if I could, and I may actually be able to if I played with this a little bit, but I'm not going to right now. What's interesting here, though, is the horizontal asymptote. It looks to me as though, again, if I zoom out, My graph is approaching 0. And again, poorly drawn, I suppose, although if I take off projector mode, it may be a little bit better. I don't know if you can still see it, but we have it approaching 0, and on this side approaching 0 as well. But of course, what's really kind of interest to me is the fact that it passes through the 0 at one point. So you want to remember that horizontal asymptotes are values that we approach as we get out to positive infinity, negative infinity. It doesn't mean that they're illegal points on our graph. It's just that's what we tend towards as we get really, really big. So again, just to follow up to the last idea, but and in this case, sorry, I have a situation where my x value, my highest power on top is x. My highest power in the denominator, if I expand this, is x squared. And so anytime we have that situation where the exponent on top is smaller than the exponent on the bottom, I'll end up with a vertical asymptote. Sorry, I was being instructed there. I think I said vertical, but when I have a higher power in the denominator than in the numerator, I end up with my horizontal asymptote, and it is always at 0. Now again, you can see in this, I just changed this to a 3, change it to a 4, change it to a 5, and whether you can tell or not, in all cases, I am actually, that's the wrong way to go. In all cases, I am actually passing through the 0 at one point, but then coming back down and approaching 0 as we get out further and further. Okay, so I think that covers horizontal and vertical asymptotes fairly well. The next example here, a little bit of a special case. If I look at this equation, I have x squared minus 4 divided by x minus 2. If you factor the numerator, of course, x squared minus 4 gives you x minus 2, x plus 2. Now this is a situation we won't run into probably in this section, but just something that we shouldn't forget. X minus 2 still tells me that x being 2 is not okay. Even though the graph seems to imply it's a nice straight line, essentially what we've done here is we've divided this by this, or factored the top. When we factor the top, we get x minus 2 times x plus 2. And of course, x minus 2 divided by x minus 2, we get a division in here that cancels out or gives me a 1. But of course, we also have to remember that x cannot be 2 still, and so if we follow this graph along, when x is 2, you'll see I do get an undefined term. So although Desmos doesn't show it, we do want to remember that this is sort of a hole in the graph at that point. Again, probably won't run into any of those in this next section because we're interested in doing the graphing, but not something that you should forget. Okay, so now finishing up, looking at the last possibility. We've gone through the possibility of having our numerators and denominator, the highest power of them being the same. And we've looked at what if the highest power in the denominator is greater than the highest power in the numerator. Well, here we have a question where our highest power in the numerator is x squared, and in the denominator is just x. And so what happens then is we get this last possibility, the oblique asymptote. And again, much like the other case, I've just kind of graphed in the asymptote here. And you can see it's basically just a straight line. And as our graph, if we zoom it out again, our graph approaches that as it heads out to x being larger and larger, x being smaller and smaller. So again, as the limit approaches positive infinity and negative infinity, our graph, which is the orange, approaches that line. Same sort of thing with the last one here. I have a slight variation on this, an x plus 1, and then my oblique asymptote ends up being 2x plus 1. Okay, so of course what we have to figure out now is how we're going to determine these things. The other ones were pretty easy to determine. This one maybe not quite as easy. So vertical asymptotes, we'll sort of really quickly here look at locations on the graph where there is not an x value. So the x value cannot be left alone or cannot be included. And again, we see that basically the denominator cannot be 0. And so x equals 0. Nope. X equals 2 is my vertical asymptote, where my vertical asymptote would be for this question. Over here, I need a little bit more work first. If I look at factoring the denominator here, two numbers that multiply to negative 30 and add to negative 13, x minus 15, x plus 2. And so my vertical asymptotes would be at x equals positive 15 and x equals negative 2. Okay, so vertical asymptotes, again, should be able to determine just by looking at the question, possibly doing a little bit of math to figure out, but we're always looking for that division by 0, and we want to make sure we don't allow for that. Horizontal asymptotes, again, when we have anything where the higher power of the numerator and denominator are equal, the limit ends up being the coefficient of the two terms. So looking at this one, these are my highest powers, numerator and denominator. They are the same. And so again, as when I put in extremely large numbers here, something like 1,000 or 1,000,000, let's say, I put in 1,000,000 and square it. I put in 1,000,000 and square it. I get 2, what's that, trillion divided by 8 trillion. And then I subtract numbers like 6 million and 17 million from those. These values become insignificant in the calculation. And the larger our numbers get, we get closer and closer to 2 over 8, or sorry, 2x squared over 8x squared, which essentially implies that our horizontal asymptote will be at 2 over 8, or 1/4. And then, again, as we sort of said down here, last possibility, if the high power in the denominator is greater than in the numerator, this is going to be a much bigger number than this is, and so our horizontal asymptote is at 0. Okay, so that's the stuff we've seen before. What if the high power of the numerator is greater than the power of the denominator? And the key here is we're talking about by 1 specifically. You may see later on by 2 and by 3, and you can probably guess what will happen, but we won't worry about that for now. We get oblique asymptotes. And so essentially, when we looked at the two examples here, I gave you what the asymptote was going to be without really explaining how I determined it. The question itself, though, 2x squared plus 3x minus 1 divided by x, or sorry, over x, can be considered a division. And so what we'll do is we'll actually do that division to determine what our oblique asymptote is. Okay, so here I'm dividing. It's a pretty simple division, really. I can rewrite the question as 2x squared over x plus 3x over x minus 1 over x, and then simplify each of these terms, and I get down to that thing. And what you see is, since we're looking at it as we get x values that are extremely large and or extremely small, when I put in extremely large numbers here, 1 divided by 10,000, 1 divided by 1 billion, this gets very close to 0 and again becomes insignificant to the question. And so the remaining part here ends up being my asymptote. And this is just the graph off the other page. And the asymptote is dotted, 2x plus 3. Of course, the rest of what's going on here will be determined some other way. It looks like there's a vertical asymptote here at 0, but as far as the oblique itself goes, that's what we're going to do. Second example was the 2x squared plus 3x minus 1 over x plus 1. And again, we're sort of looking at the highest power of the numerator, the highest power of the denominator. These will always determine whether we're talking horizontal, what type of horizontal, or oblique. As we just said, this is really saying divide these two values, and so we'll go ahead and divide them. I'm using long division. You can do this, of course, with synthetic division if you're more comfortable with that, depending on how tough the question gets. The questions you see should all be synthetic divisionable. Long division is still my preference, just because sometimes we end up with questions that are a little bit too hard for synthetic. So if this were a cubic function, divided by a quadratic function. I don't know how to do that with synthetic, but I can do it with long division just as easily as this question. And so I go ahead and do the division. X plus 1 divides into 2x squared plus 3x. It's been a while probably since you've done it, but 2x times. I'm just looking at my highest term. I need that x to go into 2x squared. It'll go 2x times. And then I multiply through. 2x times 1 is 2x. 2x times x is 2x squared. Subtract. And we get x minus 1. X plus 1 divides into x minus 1 one time successfully. And then I have a remainder of negative 2. And again, that negative 2 becomes pretty insignificant or completely insignificant as we continue on. So essentially what we're saying is we have 2x plus 1, and then we have a negative 2 divided by, and this still needs to be divided by an x plus 1. As our x values get extremely large, we have a minus 2 divided by some really big number, which is again just 0. And so we can pretty much drop the remainder. The reason for it, though, is because it still is divided by this number in the long run. And of course, the 2x plus 1 becomes now my asymptote, and I've drawn it in here. Again, copied and pasted from the other, from Desmos, really. Tried to cover that up with my line and didn't do the best job. That's a bit better.